In this video, we're going to discuss the rules for filling electrons properly into a box diagram. At this point, you should already have watched the video on what box diagrams are and how they work. Otherwise, what we're about to talk about is not going to make a whole lot of sense. If you haven't seen the video, go back, watch the original video, then we'll talk about these filling rules. Let's go over a quick list of learning objectives. First, we're going to do a quick review of what a box diagram is and what their uses are for. Then we're going to talk about a quick equation for determining number of electrons, and then we'll jump right into the actual filling rules themselves. There are three of them to worry about. They are the Aufbau Principle, Hunds Rule, and the Pauli Exclusion Principle. And with these three rules, you should be able to accurately place the correct number of electrons into any box diagram. Let's begin with a recap of what we've talked about before. We see on the left here an image of the Bohr model itself, and we've talked about the fact that while this model has its applications, it is not very valuable for us in terms of making good electron configurations that have good capabilities for predicting atom behavior. Instead, we've been moving now towards this new model, which we refer to as a box diagram. And in a box diagram, basically what we've done is we've replaced those complicated pictures of orbitals with these individual boxes, each box representing one orbital, each orbital being capable of holding 2 electrons. Just like we were able to fill electrons into this picture over here with Bohr, we should now be able to fill electrons into this picture using the rules we're about to discuss. Before we can start the actual filling process, the thing you need to know is how many electrons do you actually need to be able to fill. The equation we have down below is a review of an equation we talked about back in the atomic structure chapter, and that's the fact that the charge of an atom is equal to its number of protons minus its number of electrons. Charge you should get from the actual symbol of the atom. Number of protons we can get from our periodic table, and then finally number of electrons is what we want to search for. If you're interested in it, we can actually have a specifically made equation here where we have it solved for the number of electrons. I prefer to have one equation to handle all situations, but if you'd rather use this one, that's absolutely fine. Now we're ready to move ahead and start talking about the actual filling rules themselves. And we're going to do this in the context of an example using this atom right here, oxygen with a charge of -1, known as the peroxide ion. To start us off, we need to figure out the number of electrons we're going to be placing into our box diagram here on the right. As before we just talked about, the equation there would be the charge, which in this case is -1, denoted by the actual symbol, is equal to the number of protons, which is 8, told to us by our periodic table, minus some number of electrons E. You can use some very quick algebra to solve this, and we find out that our number of electrons in this case is going to be equal to 9 electrons. So that means we're going to need to place 9 arrows over here into our actual picture. Where those arrows go is therefore determined by the actual rules we're about to discuss. Our first rule is known as the Aufbau Principle, and the Aufbau Principle tells us that our electrons are always placed in the lowest available energy level. Energy levels are denoted in order as they're placed on the actual diagram, meaning the lowest energy level is the lowest one in the picture. That being said, our first electron should be placed right here in the first box for 1s. And we can draw a little arrow representing that. If you recall from the previous video, we use arrows to denote the locations of electrons. Our second rule we're going to deal with is known as the Pauli Exclusion Principle. The Pauli Exclusion Principle says that paired electrons always have to have opposite spins. When we go to place our second electron in our model here, we remember from previous videos that each box holds 2 electrons. We cannot move up to the second one before the first box is full. That is Aufbau's principle. Pauli Exclusion Principle then says that if we want to pair these guys up, that second electron we would place in our box is going to have a downward spin, which we denote by showing a downward facing arrow. Without getting into too much detail about what spin really is, the reason electrons have spin is because when you place 2 electrons in one orbital, they are naturally going to repel one another. Having opposite spin characteristics means that repulsion force is going to be reduced slightly, meaning it's easier for the atom to put and keep those 2 electrons in that one particular orbital. Moving along, we can continue to use the Aufbau Principle and the Pauli Exclusion Principle to continue this process. According to Aufbau, our next available lowest energy level is now 2s, where we can place an electron there, and then we can place our fourth out of our 9 electrons here to get the filled 2s orbital. We can then continue this process by placing another electron in this level up here, but now all of a sudden we're faced with a new situation. We have multiple boxes to choose from to place our next electron. The question is where should that next electron go? This brings us to our final rule, which is known as Hunds Rule. And what Hunds Rule states is that electrons at the same energy level will always fill an empty orbital before pairing with another electron. We've already talked about the fact that electrons repel one another. If you have multiple open orbitals at one level, you would expect the atom to use the open orbitals first before going through that pairing process. That being said, we have what? 1, 2, 3, 4, 5. Our sixth electron, therefore, would be placed here. Our seventh electron will be placed here. Now, we've gotten to a point where we've half-filled all of our orbitals. We cannot move up to 3s until these orbitals are full, meaning now, according to Hund's rule, we're forced to go back and start pairing these up. So that was what? 1, 2, 3, 4, 5, 6, 7. This would be our 8th electron, and this would be our 9th electron. And according to the number of electrons we determined before, that's the maximum number of electrons needed for our peroxide ion. So this then would be a completed box diagram for our peroxide ion, following our 3 very simple rules to tell us where to place each individual electron. To wrap this up, we have one more example to try, and that's to do the same exact process, but this time with the nickel ion with a +2 charge. To start us off, we're going to need to determine the number of electrons we're dealing with in nickel. Again, our charge in this case is +2. That's going to equal to the number of protons in nickel, which is 28, minus a certain number of electrons. Again, we can do some pretty quick algebra, and we can find out that our number of electrons in this case is going to be 26. That means in our diagram, we're going to need to place 26 electrons, again, using our filling rules. Well, our first electron always gets placed in the first 1s orbital. That's the Aufbau principle, and then we have to pair an electron with it using Pauli's exclusion principle. That's 1, 2. We can then continue to say our third electron would go here. Our fourth electron would have that opposite spin. Our fifth electron would get placed up in this box up here, and then we'd have to go 6, 7 to half fill all of them, and then we go start the pairing process to go 8, 9, and 10. Now you might be saying to yourself, what the heck's the point of Hund's rule if we're just going to fill up all the boxes anyway? Well, the reality of the matter is we don't always fill up all the boxes, and when we don't fill all the boxes, using Hund's rule versus not using Hund's rule will get us different answers. And scientifically or experimentally, Hund's rule is what we actually see when we're dealing with atoms themselves. Anyway, let's continue. We've got our first 10 electrons placed. Here would be electron 11 and electron 12. Electron 13, 14, 15, 16, 17, and 18. You might have noticed that I've now switched to drawing what are known as half arrows. They are simply faster to draw than drawing arrows with the double head on them. Anyway, we've gotten ourselves up to 18. This will bring us to 19 and 20, again using our rules. And now we have 6 electrons left to place. That's going to be 21, 22, 23, 24, 25, and electron number 26. And what we can see from this configuration then is that we end with a configuration with 1 pair of electrons and 4 lone electrons. And it's those 4 lone electrons that are going to govern all of the chemistry that goes along with this particular nickel +2 ion. Now, just as one last quick example, had we not bothered to use Hund's rule, we would have just done this. 1, 2, 3, 4, 5, and 6. That would have got us the last 6 electrons we needed, and we would have gotten a very different configuration with 3 pairs as opposed to what we actually had here. This is why we need to follow Hund's rule. The atom's chemical behavior does not match this configuration, therefore we need to fill them in the proper way. So that's pretty much it for this video. It's nice and quick. Based on what we've just talked about, you should now be able to determine the number of electrons in any atom or ion using that very simple equation. And then finally, you should be able to use a blank box diagram and the 3 filling rules in order to accurately place electrons into the diagram itself. Later on, we're going to talk about how you can build your own box diagram to fill, and also we're going to spend more time talking about how you can use these box diagrams in order to understand the chemistry associated with your particular atom.